Kummersdorf Proving Grounds, Germany, March 19th, 1943. Dawn light filters through reinforced glass windows of testing Bay 7, illuminating concrete walls scarred by years of weapons trials. 3 Wehrmacht officers stand watching a captured American tank idle in place, the rumble of its engine echoing off the walls. The machine is an M4 Sherman medium tank, hauled here 6 weeks ago after being knocked out near Sidi Bou Zid in Tunisia during the disastrous American debut at Kasserine Pass. The tank bears scorch marks from the hit that disabled it. An 88mm round from a Tiger punched through the right sponson, killed the loader, and sparked a fire the crew extinguished before abandoning the vehicle. German recovery teams found it 3 days later, still smoldering but structurally intact. They patched the hole, replaced burned wiring, topped off fluids, and the engine started on the first attempt. That was 6 weeks ago. The Sherman has been running nearly continuously since then. One of the officers, a 41-year-old engineer named Klaus Weber from the Waffenamt Ordnance office, climbs onto the rear deck. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. He signals the German driver inside to rev the engine. The Ford GAA V8 responds instantly, settling into a steady growl that barely vibrates the hull. Weber places his hand flat on the engine deck. He can feel the heat, but not the violent shaking that characterizes German tank engines under load. He's been testing captured enemy equipment for 2 years. Soviet 34s with their crude but effective designs. British Matildas, slow but reliable. Lend-Lease Valentines that somehow kept running despite minimal maintenance. But this American machine unsettles him differently. It's not what the Sherman does that bothers him, it's what it doesn't do. It doesn't break. The Sherman has been running continuously for 6 hours today. No overheating, no oil pressure drops, no transmission grinding that would make a Panther crew wince. Just that persistent mechanical hum of a machine doing exactly what it was designed to do, hour after hour. Weber climbs down and consults his notes. According to the maintenance logs captured with this tank, logs maintained by a Sergeant Morrison, this specific Sherman had travelled over 4,200 miles before being knocked out. 4,000 miles on the original transmission. Weber has compared this against German data. A Panther transmission was considered exceptional if it reached 1,500 miles before major overhaul. More often, final drives failed after just 93 miles. This Sherman's transmission has covered 44 times the distance of an average Panther final drive. Weber has checked the maintenance logs repeatedly, looking for evidence of transmission replacement. Nothing. Just regular oil changes every 500 miles, filter replacements every 1,000 miles, routine adjustments, but no transmission work. The powertrain installed at Chrysler Defense Arsenal in November 1941 was still functioning perfectly in February 1943 when an 88mm round ended its service. Albert Speer, Reich Minister of Armaments and War Production, visited Kummersdorf the previous week. Weber had prepared a demonstration of captured Allied armour. Speer arrived with ministry officials, factory representatives from MAN and Henschel, and several panzer generals, including Heinz Guderian. They inspected a Soviet 34 first. Guderian pointed out its sloped armour and powerful gun. Factory representatives noted its crude construction. Everyone agreed it was dangerous but beatable with proper tactics and superior German engineering. The British Cromwell drew less interest. Fast, well-made, but undergunned. Then came the Sherman. Weber had the driver start the engine. The Ford GAA caught immediately, settled into that smooth idle. One of the Henschel engineers actually flinched. That reaction came from contrast. He was accustomed to Maybach engines requiring careful warm-up, coughing and sputtering before finding rhythm. The Sherman just ran, quiet enough that conversation continued normally. Speer climbed into the commander's position and sat there for several minutes, studying the interior layout, the visibility, the communication system. When he climbed out, his expression was troubled. Weber walked them through the technical briefing. The Sherman's design philosophy prioritized reliability over performance. It used proven automotive components scaled for military use. It was designed for production by workers with limited training. Maintenance could be performed by conscript soldiers following basic procedures. Then Weber presented the data on transmission life. 4,000 miles on this example. Multiple examples in British service exceeding 3,000 miles. No reports of catastrophic transmission failure. Mean distance between overhauls estimated at 5 to 8,000 miles. The room went silent. A general asked the obvious question. "Why can't we build transmissions like this?" Weber explained. The Sherman transmission used herringbone-cut gears, requiring specialized equipment allocated to U-boat and aircraft production. The materials required high-grade alloy steels. Germany's alloy production was stretched thin. Molybdenum and nickel were unavailable. More fundamentally, the Sherman embodied mature automotive engineering. America had built synchromesh transmissions for 20 years. The manufacturing knowledge existed before the war started. Speer listened and finally spoke. "We've been building tanks the wrong way. The Americans build tanks that work. We build tanks that impress. They will win because working beats impressive." The meeting broke up shortly after. But knowing didn't help. Speer couldn't create machine tools or alloy steel from nothing. By March 1943, Germany's industrial capacity was fully committed. Retooling meant production delays Hitler would never approve. Germany had spent the war building engineering marvels. The Panther featured torsion bar suspension, Zeiss optics, a 75mm gun that could penetrate enemy armor at extreme ranges. On paper, the Panther was the finest medium tank of World War II. In practice, Panthers spent more time disabled than fighting. Operational readiness rates between 20 and 40% were common in early 1943. The Tiger embodied similar contradictions. Devastating gun, thick armor, terrifying reputation, but it was a 70-ton mechanical monstrosity consuming fuel catastrophically, breaking down constantly. A Tiger had maximum road range of 110 kilometers, 68 miles. In combat conditions, actual range dropped to perhaps 50 kilometers. A Tiger sent to battle 30 miles away might not have fuel to return. The Germans designed tanks for tactical perfection, for ideal combat scenarios where the tank engaged enemies at long range using superior optics and firepower. In that ideal scenario, German tanks were unbeatable. War never provided that scenario. Combat meant road marches wearing out components, mechanical issues developing mid-battle, maintenance by exhausted crews using whatever tools they could find. The Sherman was designed for worst-case scenarios. The engine needed to start in North African heat and Russian cold. The transmission needed to survive untrained drivers grinding gears. The suspension needed to handle roads that were barely trails. Every component was overbuilt for conditions that would destroy equipment designed to minimum specifications. Before the Sherman fired a shot, before American troops waded ashore in North Africa, the United States faced a paralyzing problem. In 1939, total American medium tank production numbered 18 units, 18 tanks for the entire year. The German Wehrmacht rolled into Poland with approximately 2,800 tanks. The U.S. Army owned 66 medium tanks by June 1940. France fell that same month. Roosevelt understood the mathematics. America would fight. The question was whether it would fight with weapons that worked. The automotive industry was the answer. Detroit had perfected mass production. Henry Ford's assembly lines could pump out a Model T every 24 seconds. Chrysler, General Motors, Ford employed hundreds of thousands of skilled workers who understood metal fabrication, engine assembly, powertrain construction. William Knudsen, who'd run General Motors before Roosevelt recruited him for war production, understood something the generals didn't. The principles of mass production transfer. Components remain components, whether moving down a car assembly line or tank production facility. The key isn't complexity, it's standardization. In August 1940, Knudsen called K.T. Keller, Chrysler's president. Could Chrysler build tanks? Not dozens, thousands. Keller said yes. Within weeks, Chrysler broke ground on Detroit Tank Arsenal in Warren, Michigan. The factory design came from Albert Kahn, who'd created Ford's River Rouge complex. Kahn understood industrial flow. Raw materials entered at one end, finished products emerged at the other. Detroit Tank Arsenal covered 113 acres. The main assembly building stretched longer than 3 football fields. Rail sidings ran directly into the facility. Construction began in September 1940. The first M3 Lee rolled out in April 1941, 7 months from breaking ground to producing combat vehicles. That timeline was impossible by European standards. But Chrysler wasn't building a tank factory. They were replicating an automobile plant with a different end product. The M3 Lee was always a stopgap. Its hull-mounted gun had limited traverse. The tall profile made it easy to target. But the M3's real value was educational. Chrysler workers learned to assemble armored vehicles. Engineers discovered which automotive components transferred to military use. By the time the M4 Sherman entered production in October 1941, Detroit Tank Arsenal had refined its processes. The Sherman's powertrain embodied automotive thinking, applied to military requirements with deliberate simplicity. The transmission was a 5-speed synchromesh unit, identical in fundamental principle to transmissions found in any American heavy truck or commercial vehicle of the era. First gear provided what mechanics called a granny ratio of 7.56 to 1. This extremely tall gear gave enormous mechanical advantage for specific situations, climbing steep obstacles that would stall other vehicles, starting the tank with maximum combat loads, pulling disabled vehicles, pushing through deep mud or water crossings, descending steep slopes where engine braking was essential to prevent runaway. In first gear, a Sherman crawled at barely 1 or 2 miles per hour, but it moved with the kind of torque multiplication that could overcome almost any resistance. Second gear, at 3.1, 1 to 1, was the normal starting gear on level ground. Drivers used second to get the 30-ton tank moving from a standstill, accelerating smoothly up to perhaps 5 miles per hour before shifting to third. This gear saw constant use in combat, where frequent stops and starts were routine. Third gear, 1.78 to 1, covered speeds from 8 to 12 miles per hour. This was the gear for cross-country movement through moderate terrain, the steady grinding advance through French bocage country or North African wadis, where maintaining formation mattered more than speed. Fourth gear, at nearly 1-to-1 ratio of 1.11, represented normal tactical movement speeds, 13 to 19 miles per hour depending on terrain and load. Most combat operations happened in fourth gear. It provided enough speed for approaching objectives, maneuvering during engagement, or withdrawing under fire without sacrificing mechanical advantage. Fifth gear was actually an overdrive gear with a ratio of 0.73 to 1. The transmission output shaft rotated faster than the input from the engine, allowing higher speeds without over-revving. Fifth gear was strictly for road marches on improved surfaces, where a Sherman could theoretically reach 26 miles per hour, though most experienced drivers kept it under 22 to preserve engine life. Reverse gear at 5.65 to 1 was nearly as tall as first gear forward. This deliberately limited the tank's reverse speed, a weakness German tankers learned to exploit. A Panther could reverse nearly as fast as a Sherman could advance. But the trade-off gave the Sherman stronger mechanical advantage for extricating itself from obstacles. The critical innovation was synchromesh operation in gears 2 through 5. Synchromesh technology, which had been standard in American passenger cars since the mid-1930s, used brass synchronizer rings to match gear speeds before engagement. This eliminated the need for double clutching, that awkward technique where you clutch once to neutral, release the clutch to let engine speed adjust, then clutch again to engage the next gear. For tank operation over long campaigns, synchromesh was transformative. It reduced driver fatigue dramatically during road marches that could stretch for days. It reduced training time since recruits with basic driving knowledge could learn Sherman operation in days rather than weeks. Most importantly, it reduced wear on gear teeth and shift linkages because properly synchronized shifts imposed minimal shock loads on the transmission components. First and reverse gears weren't synchronized, but they didn't need to be. First gear was typically engaged from a standstill when gear speeds already matched. Reverse likewise engaged from stopped positions. Wear patterns on captured transmissions examined at Kummersdorf proved this design choice was sound, showing minimal damage to first and reverse gear teeth despite years of hard operation. The transmission case was cast iron, a deliberate material choice that German engineers initially dismissed as crude. But cast iron provided several advantages: excellent wear resistance for long service life, effective vibration damping for quieter operation. Most critically, cast iron was easy to manufacture in volume using existing foundry capacity. Every major American city had foundries capable of casting transmission cases to specification. Chrysler could source cases from multiple suppliers simultaneously, eliminating production bottlenecks. German transmissions used more exotic aluminum alloys that required specialized casting facilities, creating supply constraints that limited production. The gears themselves were cut from high-grade alloy steel, precisely machined on modern gear cutting equipment, then heat-treated to achieve specific hardness profiles. This was where American manufacturing superiority became absolutely decisive. The United States possessed more and better gear-cutting machines than any nation on Earth. The machine tool industry, concentrated in Cincinnati, Cleveland, and Detroit, had been supplying the automotive industry's voracious appetite for decades. When war came, that enormous installed capacity transferred directly to military production without requiring new investment or retooling. Each gear was finish ground after heat treatment to achieve tolerances measured in thousandths of an inch. This precision machining reduced operational noise, improved mechanical efficiency, and dramatically extended service life. Late-war German gears, as material quality degraded and bombing disrupted heat treatment facilities, couldn't match these manufacturing specifications. The difference showed up first in noise levels, ultimately in catastrophic transmission failures. The final drives used herringbone-cut gears, those distinctive assemblies with V-shaped teeth meeting at the center line. Herringbone gears provided multiple advantages over the straight-cut designs German engineers were forced to adopt. They ran significantly quieter because the angled teeth distributed loads more evenly across the tooth face. They produced less axial thrust, meaning less wear on supporting bearings. They handled slight misalignments better, critically important in combat vehicles subjected to shell impacts and violent maneuvers. Most importantly, herringbone gears were substantially stronger for a given size, because more tooth surface remained engaged throughout the rotation cycle. The entire powertrain shared a common lubrication system containing 152 quarts of oil, an enormous quantity that shocked German engineers accustomed to more modest oil capacities. The oil was pumped under pressure to critical bearings that needed continuous lubrication under heavy loads. After lubricating bearings, the oil splash lubricated gears as it drained back into the sump, ensuring every moving part received adequate protection. An oil cooler mounted on the rear firewall of the fighting compartment maintained acceptable operating temperatures even during sustained combat operations that generated tremendous heat. The cooler was a simple heat exchanger using engine cooling air, requiring no additional power source or complex controls. This cooling system prevented oil breakdown that would lead to accelerated wear and eventual catastrophic failure. Oil specifications were deliberately standardized to commercial grades: SAE 50 weight for normal temperature ranges, SAE 30 for extreme cold environments like Russian winters or Alaskan operations. These were off-the-shelf petroleum products available anywhere with basic refining infrastructure. Sherman tanks could be serviced in Britain, North Africa, Italy, France, or the Pacific, using locally available lubricants. German tanks often required specialized military-grade oils that chronically short supply systems struggled to deliver, creating situations where operational tanks sat immobilized, waiting for correct lubricants. The design tolerance for the complete powertrain was 25,000 miles before major depot-level overhaul. That figure wasn't an aspirational goal written into procurement contracts. It was the minimum acceptable service life that procurement officers demanded contractors guarantee. Early production Shermans fell somewhat short of that ambitious target, primarily due to clutch problems and manufacturing inconsistencies as production ramped up rapidly. By 1943, after systematic engineering refinements and improved quality control procedures, powertrains regularly exceeded the specification, with some examples documented at over 30,000 miles on original components. German engineers at Kummersdorf knew these numbers. Captured maintenance logs told them. What they couldn't understand was how Americans achieved reliability without sophistication. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Panther's AK 7-200 transmission was a 7-speed masterpiece manufactured by Zahnradfabrik Friedrichshafen. It featured advanced synchromesh, sophisticated steering brakes, neutral steer capability. On paper, cutting-edge technology. In practice, catastrophic. Third gear consistently stripped under load. Steering clutches wore out rapidly. Final drives, simplified from planetary designs to straight-cut gears due to machine tool shortages, failed on average after 150 kilometers in French post-war service. Half of abandoned Panthers in Normandy showed final drive failures as the cause. The Tiger's transmission was more robust, but even Tigers suffered chronic problems. Fuel pump failures, engine fires from leaking seals, suspension components wearing out faster than supply chains could replace them. The fundamental problem wasn't engineering skill. German engineers were brilliant. The problem was philosophy. German designers created systems optimized for peak performance, for best-case scenarios. Good roads, adequate maintenance time, trained crews, ample spare parts. When any condition failed, which they always did in combat, systems collapsed. American designers created systems optimized for worst-case scenarios. They assumed terrible roads, minimal maintenance time, hastily trained crews, supply line chaos. The Sherman's powertrain worked under those conditions because it was designed for those conditions. Weber's team spent 3 weeks studying the captured Sherman's transmission. They disassembled it completely. They measured gear tooth profiles. They analyzed bearing types. They calculated gear ratios and load distributions. They examined every component, trying to find the secret. There was no secret. The Sherman transmission was undergraduate mechanical engineering executed with extraordinary precision. The gears were cut on modern machine tools to tolerances tighter than German standards. The materials were high-quality alloy steels, consistently heat-treated. Assembly was straightforward, designed so moderately skilled workers could do it correctly. What truly separated American and German approaches became clear when Weber examined maintenance procedures. The Sherman's powertrain was designed to be removed and replaced as a complete unit. 6 mounting bolts secured the transmission. The drive shaft disconnected with a simple coupling. An armored recovery vehicle could pull a damaged powertrain and install a replacement in under 4 hours. The Panther's transmission required removing the entire front hull. The driver's compartment had to be disassembled. The repair demanded specialized tools and trained mechanics in a rear echelon facility. Field replacement was impossible. Combat damage to the transmission meant losing the tank until it could be recovered and hauled to a depot. This difference rippled through every aspect of operations. American tank battalions maintained high operational readiness because broken tanks got fixed quickly. German panzer divisions watched their strength dwindle as vehicles accumulated in repair queues. Weber compiled his findings into a technical report. The conclusions were stark. The Sherman's transmission succeeded because it embodied mature automotive engineering, benefited from superior machine tools, and reflected a design philosophy prioritizing maintenance ease over technical sophistication. Could Germany replicate it? Practically no. Replicating required machine tools Germany lacked due to Allied bombing. It required alloy steel Germany was rationing. It required abandoning years of development. It required admitting simple beats sophisticated. None of that happened. The Panther continued production with its troublesome AK-7-200. The Tiger II emerged with an even more complex transmission. Germany kept building technically superior tanks that spent more time broken than fighting. Meanwhile, American production accelerated beyond what German planners thought physically possible. 11 separate facilities across the United States manufactured Sherman variants simultaneously. These weren't small workshops but massive industrial complexes, each capable of producing hundreds of tanks monthly. Detroit Tank Arsenal, the crown jewel of American tank production, alone produced 22,207 tanks between 1941 and 1945. That single facility's output exceeded Germany's total production of Panthers, Tigers, and King Tigers combined. Chrysler's efficiency improvements became legendary within military procurement circles. They got so proficient at tank production that they systematically reduced costs below contracted prices, then wrote checks back to the United States government, totaling millions of dollars for coming in under projected per-unit expenses. This was completely unheard of in defense contracting, where cost overruns were standard and expected. The fact that a private contractor was voluntarily returning money to the government because they'd become too efficient shocked Washington bureaucrats. By mid-1943, total American Sherman production reached 2,000 tanks per month, flowing from all facilities combined. 2,000 30-ton combat vehicles every 30 days. To put that in perspective, Germany's entire tank production for all models, Panzer IVs, Panthers, Tigers, assault guns, totaled roughly 500 to 700 units monthly at peak capacity. That production number represented more than raw manufacturing capacity or industrial might. It represented a fundamental philosophical difference in how America and Germany conceptualized and executed industrial warfare. Germany built tanks the way medieval guilds built suits of armor. Each piece was crafted by skilled artisans who understood their specific trade. Every tank was somewhat unique, requiring individual attention and specialized knowledge. Components weren't truly interchangeable. Replacing a damaged part often meant fabricating a new one or modifying a standard part to fit that specific vehicle. The vehicles were irreplaceable masterworks. America built tanks the way Henry Ford revolutionized automobile manufacturing, interchangeable parts manufactured to exacting tolerances that guaranteed any part would fit any vehicle. Trained operators following standardized procedures could perform complex assembly operations reliably after brief training. Components flowed through meticulously optimized facilities, where every movement, every tool, every workstation had been studied and refined for maximum efficiency. The vehicles were intentionally replaceable, designed from the beginning to be produced by the thousands using workers with modest skill levels, following clear procedures. The strategic implications were decisive. When American tank battalions lost vehicles, replacements arrived within weeks. When German panzer divisions suffered losses, those losses were permanent. Americans could afford attrition. Germans couldn't. Between 1942 and 1945, American factories produced 49,324 Sherman tanks. Germany produced approximately 6,000 Panthers and 1,300 Tigers and King Tigers combined. The raw production ratio favored America 6-1, but production only matters if vehicles reach combat and remain operational. American Shermans deployed with operational readiness rates consistently above 90%. German Panthers in 1943 averaged 20 to 25% operational readiness. Even by mid-1944, Panther readiness rarely exceeded 70%. Those percentages represent human consequences. An American armored division with 300 Shermans could expect 270 tanks available for combat on any given day. A German panzer division with 200 Panthers and Tigers might field 70 functional vehicles. The math of attrition became simple. America could replace losses. Germany couldn't. The transmission failures cascaded into systemic collapse. A Panther with a broken final drive couldn't move. It couldn't be repaired in the field. It required recovery, assuming recovery vehicles were available. Then transport to a depot, assuming the depot existed. Then waiting for parts, assuming parts existed. Meanwhile, combat continued. The disabled Panther's crew might receive a replacement, but probably not. German production couldn't keep pace. More likely they'd be reassigned to infantry duty. Their training, experience, preparation became irrelevant because a transmission gave out. Contrast that with American procedures. A Sherman throws a transmission in combat. The crew disables the tank and withdraws. That night, or the next day, an M32 armored recovery vehicle arrives. The crew removes 6 bolts, disconnects the drive shaft, uses a winch to pull the damaged powertrain out. They install a replacement from depot stock. 6 bolts, reconnect the drive shaft, top off fluids. The tank returns to service. Total downtime, 4 to 8 hours. The tank stayed with its unit. The crew stayed with their tank. Operational strength remained constant. That was the Sherman's real advantage. Not tactical superiority, but logistical resilience. German commanders understood this intellectually but couldn't solve it practically. Speer pushed for simplified, reliable designs. He saw the Sherman at Kummersdorf. He read Weber's reports. He recognized Germany was losing the reliability war, but changing course required halting production lines, retooling factories, accepting short-term output reductions. Hitler refused. The Führer demanded more Tigers, more Panthers, more technologically advanced vehicles to match his vision of German superiority. Practical concerns like maintenance didn't interest him. He wanted weapons that inspired fear, not weapons that worked. This strategic blindness infected the entire German war effort. Engineers designed ever more sophisticated systems, the Maybach HL 234 engine with improved cooling, the Tiger II with its long 88mm gun. Each new design addressed battlefield performance while ignoring the reality that performance means nothing if the vehicle doesn't reach the battle. The Panther's final drive problem exemplifies this disconnect. German engineers knew from the beginning that straight-cut final drive gears were inadequate. The original design specified planetary gearing, but Germany lacked gear-cutting machine tools to produce planetary systems in volume, so they simplified to straight-cut gears, knowing they would fail prematurely. The solution was obvious: reduce the Panther's weight or increase final drive strength. Instead, they taught drivers to avoid certain maneuvers. Pivot turns placed too much stress. High-speed turns wore them faster. Drivers learned to baby their tanks, treating them like temperamental race cars rather than combat vehicles. American tankers drove Shermans like trucks. They pivot-turned. They crashed through hedgerows. They forded streams. The transmission took it because it was designed to take it. The synchromesh gears could handle abuse. The herringbone final drives distributed loads evenly. The whole system included safety margins that German engineers considered wasteful. Those safety margins were the point. American designers assumed worst-case scenarios: poorly trained operators, inadequate maintenance, missing lubricants, contaminated fuel, damaged roads, sustained operation without rest. They overbuilt every critical system to survive conditions that would destroy vehicles designed to tighter specifications. This approach appeared wasteful to efficiency-focused German engineers. Why make components heavier than minimum requirements? Why include redundant systems? Why design for abuse instead of proper operation? The answers came from understanding industrial warfare's actual demands, not theoretical ideals. American standardization looked boring but proved decisive. The Sherman's powertrain fit multiple variants with minimal changes. The Ford GAA V8 engine also powered the M10 and M36 tank destroyers. Maintenance personnel trained on one Sherman variant could service any Sherman variant. German diversity became a logistical nightmare. The Tiger and Tiger II shared almost no components. The Panther used different engines, transmissions, road wheels than the Panzer IV. Each vehicle type required separate supply chains, separate maintenance training, separate depot facilities. By March 1945, a desperate meeting of the Panzer Commission revealed just how catastrophically German transmission problems had become. General Thomale, responsible for Panzer Force readiness, stood before assembled officers and delivered a devastating assessment. Orderly utilization of tanks had become impossible due to final drive failures. The numbers were staggering and spoke to systemic collapse rather than isolated problems. Prior to the Eastern Offensive in early 1945, 500 defective final drives plagued the Panzer IV fleet. These weren't new tanks with manufacturing defects. These were veteran vehicles whose final drives had simply worn out faster than supply systems could provide replacements. The Panther Force showed 370 known final drive failures. Even the Tiger, with its more robust planetary final drives, reported roughly 100 failures. Units across every front were abandoning otherwise functional tanks, vehicles with working engines, undamaged armor, functional weapons, simply because the final drives had failed and no replacements existed. The psychological impact on crews was devastating. Tankers lost confidence not in their own skills but in their equipment. Every combat mission carried the knowledge that mechanical failure was more likely than enemy action to end their tank's combat effectiveness. When final drives failed during combat, crews increasingly abandoned entire vehicles rather than waiting for recovery and repair that might never come. This represented psychological defeat as profound as any tactical loss. German soldiers no longer trusted the machines their nation had spent years engineering and building. German tankers no longer trusted their equipment with good reason. They knew from bitter experience that their Panthers would break during approach marches. They understood their Tigers consumed fuel so voraciously that return trips from objectives were always questionable. They'd watched too many comrades die not from enemy shells, but from being stranded in disabled vehicles that became targets. Mechanical failure wasn't an occasional problem anymore. It was the expected outcome of every extended operation. American tank crews developed completely different psychology around their equipment. They trusted their Shermans, not because Shermans were invulnerable to enemy fire, they absolutely weren't, but because Shermans were utterly predictable in mechanical behavior. The tank would start reliably every morning. It would run consistently throughout the day. It would complete assigned missions without unexpected mechanical failures. When crews worried, they worried about enemy fire, minefields, tactical situations. Mechanical failure simply wasn't a primary concern because it rarely happened. The Ardennes offensive in December 1944 demonstrated these reliability problems with catastrophic clarity. German operational planning, done by experienced staff officers who understood their equipment's limitations, assumed 20% mechanical failure rates during approach marches. This wasn't pessimism, it was realistic assessment based on years of experience. For every 5 tanks starting an operation, planners expected one to break down before reaching the battlefield. Actual failure rates during the Ardennes approach exceeded even these pessimistic projections significantly. Panthers and Tigers broke down along narrow forest roads in the Ardennes, their bulk blocking the limited road network and preventing following units from advancing. Recovery vehicles that should have cleared disabled tanks were themselves broken or lacked fuel to operate. The famous German fuel shortages weren't just about supply lines, they reflected the reality that German tanks consumed fuel at rates that logistics simply couldn't sustain. Meanwhile, American forces were rushing reinforcements to the threatened sectors with minimal mechanical losses, despite covering comparable or greater distances. Sherman-equipped units moved from reserve positions, covered hundreds of miles through winter conditions, and arrived at the Ardennes with combat-ready vehicles. The tanks fought, withdrew when tactical situations demanded, refueled, rearmed, and fought again the next day. German tanks that actually reached the front lines often represented the sole surviving vehicles from much larger original formations. By January 1945, when the Ardennes offensive collapsed completely, investigation teams examining abandoned German equipment found something telling. Numerous tanks sat disabled not by American fire but by mechanical failure. Final drives, transmissions, engine fires from fuel system leaks, the identical problems that had plagued German armoured forces since the disastrous Kursk offensive in 1943. Except now, in 1945, Germany possessed no industrial capacity whatsoever to replace these losses or repair damaged vehicles. The Sherman kept rolling, not because it was better armed or armoured, but because it was better built for sustained operations. The transmission that German engineers studied at Kummersdorf represented American industry's fundamental understanding of modern warfare. Reliability matters more than capability. Sustainability matters more than performance. This lesson extended beyond World War II. Post-war analysis by British and American evaluators consistently emphasized mechanical reliability as the Sherman's greatest strength. The British used Shermans through the 1950s. The Israelis modified Shermans and fought them successfully in 1967 and 1973. No comparable afterlife awaited German tanks. The Panthers and Tigers were too complex, too maintenance-intensive, too parts-hungry. Even nations that captured functioning examples struggled to keep them operational. The French attempted to field Panthers post-war and found them nearly impossible to maintain. Average final drive life in French service, 150 kilometers. The transmission Weber examined at Kummersdorf in 1943 embodied principles that reshaped military vehicle design. Modern main battle tanks prioritize reliability alongside firepower and protection. Maintenance accessibility is designed in from the start. Powertrains can be swapped in field conditions. Standardization reduces logistics complexity. These weren't revolutionary concepts. They were automotive industry best practices applied to combat vehicles. The Americans did it first and most successfully, because American industry was built on those practices. Detroit had spent 4 decades learning to produce reliable vehicles in massive quantities. Germany never made that transition. German automotive industry existed, but it remained separate from military production. Tank factories followed craftsman traditions, building sophisticated machines in small numbers. This produced tactically superior vehicles that couldn't survive strategic attrition. The numbers from Detroit Tank Arsenal tell the story. 22,207 tanks produced between 1941 and 1945. Peak monthly output, over 1,000 tanks. Cost per unit decreased throughout the war as Chrysler refined processes. German tank production followed the opposite trajectory. Per unit costs increased as material shortages forced substitutions. Production rates declined as bombing destroyed factories. Quality deteriorated as skilled workers died and replacements lacked training. By 1945, Germany was producing tanks with steel so brittle that non-penetrating hits caused massive internal spalling that disabled vehicles. Quality control had collapsed. American production maintained quality through the war's end. The question Weber couldn't answer, that German engineers collectively couldn't answer, was how to replicate that powertrain with Germany's resources in 1943. The answer was they couldn't. The gap wasn't just technical. It was philosophical, industrial, and cultural. America built tanks the way it built everything, with an eye toward mass production, operator simplicity, maintenance, accessibility. Germany built tanks emphasizing technical sophistication, performance optimization, engineering elegance. In peacetime, the German approach produced better vehicles. In total war, the American approach produced victory. The Sherman's transmission was never meant to be impressive. It was meant to work, day after day, mile after mile, through mud and dust and combat and neglect. It worked. That proved more valuable than any amount of technical sophistication. Weber understood that, even if he couldn't admit it in official reports. Standing in Kummersdorf, watching that captured Sherman idle smoothly after hours of continuous operation, he knew Germany had been defeated by something more fundamental than battlefield tactics. Germany had been defeated by a transmission that refused to break. That change never came. German tanks continued breaking. American tanks continued running. The war ended with tens of thousands of Shermans still operational, many on original transmissions. Germans surrendered with panzer divisions at 20% strength, abandoned vehicles littering every retreat route across Europe. The Sherman's transmission embodied a principle that determined victory. The tank that reaches the battlefield beats the tank that doesn't, regardless of specifications. The transmission that lasts 25,000 miles beats the transmission that fails after 90 miles, no matter how sophisticated its design. American automotive engineers understood that instinctively. They'd spent decades building vehicles for customers who demanded reliability above all else. The same principle applied to tanks, except the consequences of failure were measured in lives rather than inconvenience. The Sherman's transmission represented everything German engineers had been trained to disdain, and everything German tankers desperately needed. By the time anyone in authority recognized that contradiction, recognizing it changed nothing. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.